Hello, everyone, and thank you for joining this presentation on the adaption of 3D scanning technology for high-precision bridge inspection. My name is Lexi Hain. I'm with the University of Connecticut, and the PI on the project that I've worked with was Arash Sagi. I also would like to take a moment to thank our champions at CTDOT, Armin, Bob, Ed, and Andrew. The focus of this research was to be able to overcome some of the challenges we have with traditional inspection methods and use commercially available 3D scanning technology to provide high accuracy, objective data for bridge inspection.
So first, this is the Artec LEO scanner in its Pelican case box. When we take the scanner out, this is the main screen that you will see when you're operating the scanner. And this is the side that's pointed at the beam end doing the data collection. And the battery is located at the base of the scanner. Now that we've gotten familiar with the scanner itself, we're going to focus on how do we use the scanner in the field to do an inspection of a beam with corrosion damage. This has two main parts. The first is the preparation before the scan, and the second is the actual scan itself. Starting with the preparation, the first most important thing is we need to make sure the beam is thoroughly cleaned. The beam that we're using in this trial today has been blast cleaned and then painted, so it's not a concern in this situation. But the scanner itself only captures what is visible. So if you're working on a beam that has heavy corrosion damage, has laminar rust, you need to make sure to thoroughly remove that before using the scanner. The other aspect of this beam, as it was recently painted, is that it doesn't have distinctive features of corrosion, no changes in color and texture along the beam. That's something that normally helps the scanner with tracking. So this is kind of our worst case situation where we have a uniform surface with a slight shine. So that's why today we're really going to focus on where we can put our markers to make sure that we get the best scan possible and that we're able to align it in post-processing. With alignment, there are three main tools that we use. The first is just using markers that we can write on the beam, normally an X mark or an alpha with different colors, just to help with tracking during the scan. And the second two are these alignment bars. So now we are ready to scan. We can see in our preview that we're able to capture the whole beam. I'm going to go ahead and click that trigger. We don't see the texture in this main area. What we see is green and yellow. And what that shows is the level of information that we're collecting. Green is good, but also our distances. Are we collecting enough information and are we not getting too close? If we get too close to an area, you can see it turns that red color. So what we want to do is go over all areas of interest, make sure all the holes are filled in, and make sure that everything is green. We can see, looking at the front of the stiffener, this is one of those red areas, so that shows that I'm missing information, so I'll have to go back and rescan that. To do that, I hit the scan button again, point at the beam, and since I'm in the same project, it should be able to find where I am. Once it clicks in, you'll be able to see, and then I will go back and collect that information that I need. We see that area of the stiffener is now showing up. So we want to look at any other areas that may be missing information. And in particular, we want to focus on our areas that have corrosion damage, make sure that we have all the information.
Once we've collected our data from the field, we can take this information back to the office and use our post-processing software to generate a full 3D model. This is a video of the full 3D model that we have. We can rotate it around and you can see it really is like bringing the bridge right back to the office. Using this model, you're able to extract measurements. So at certain points, this is where we can get those accurate values for the thickness. And we can do additional cool things like viewing the model in VR to give it even more of a first-person feel.
This is an example of a beam on a bridge that has been recently replaced. And this is something we can get closer, and really we can set up boundaries so we can walk all around the model. Now I want to show a few cool tools, and if you see when we look at our controller, we have a flashlight and a ruler tool. If we go ahead and click that flashlight, we can use this to inspect areas on the beam. And we can really inspect some of those areas with the heavy corrosion damage. We can also use our ruler tool, and this is something built in. It doesn't come like this, but something that we did through our research. And then we can overlay a color map, which shows the thickness. Red is the most concerning area. You can see we go down to almost 0. And then we go up to about 4 millimeters in the intact areas, which is that blue and that green. So this is really helpful for inspectors to be able to have someone go out and collect the data and then have us be able to package it so they can do their inspection from the office.
In the future, Connecticut DOT has laid out a series of both short-term and long-term goals. In the short term, they plan to perform quality assurance checks on inspections using the scanning technology, verify and obtain section loss measurements for load ratings, and obtain section loss measurements for critical bridges that face closure or posting. In the long term, they're planning on using the scanning technology in subsequent inspections to look at the rate of corrosion and how it's progressing, investigating 3D scanning for crack mapping and bridge hits, also using the technology to preserve and recreate historically significant details, and also coming up with a criteria to determine when to use scan data and when to just simply use the conventional methods. With that, I wanted to thank the Connecticut DOT for funding this work and our partners at CTDOT in both the research unit and bridge safety and evaluation.